So we have a different academic institution, including, of course, University of Belgrade, Faculty of Mechanical Engineering, also two institutions from United States, Drexel University, University of Toledo, and University of Buffalo, and also RMIT University from Melbourne. So it is a work of a group of international authors from Serbia, US, Australia. The title is Unified Help+Hede Model, Review and New Insights. What I will give in this presentation is some new experimental results and some new confirmation related to Help+Hede model published recently and called Unified Help+Hede Model between 2019 and 2024. 4 and 5 is most important. Here is the overview of hydrogen embrittlement research. But industry need reliable and accurate life damage prediction, and industry need predictive maintenance model. We still don't have that. There are a lot of reasons, but I will mention some of them. Many research related to phenomenology of hydrogen-related degradation, many research related to hydrogen source and entry into the material, and also the final things we should provide for the industrial application is some tools for prediction and for reliable operation of component exposed to hydrogen. We're working more than 10 years on that. As a conclusion, in 2024, we can say that synergistic interplay of both help. When we say help, I don't mean only hydrogen-enhanced localized plasticity mechanism, but combination of plasticity-enhanced mechanisms like Hsiao, IED, help, and Hede, or decohesion, are responsible for the failure of components, and it's confirmed by numerous experimental evidence and also through simulation and modeling in various materials. When we talk about the synergy, we have generally two proposed approaches. The first one is help-mediated decohesion model, which learned us that help is always active and help is a prerequisite for activation of decohesion at some condition. Contrary to that, our Help+Hede model proposed in 2014 tell us that synergistic effect of some or multiple plasticity enhanced mechanism, help and others, together with the Hede, are responsible for hydrogen embrittlement in steel originally proposed. And you will see on the next slide, now confirmed the almost all other metallic material, but one of them predominates under specific condition. And the concept of Help+Hede is to define when some of the mechanism predominates and what is the condition for the hydrogen-enhanced localized plasticity or other plasticity-mediated mechanism to be predominant, and when that transition happens and when the cohesion became dominant. As you can see here, I list almost all materials in which the synergistic interplay according to Help+Hede model is confirmed. So we have all kinds of steels. But recently, also iron and nickel. Recently, it is confirmed in aluminum alloys. More recently, in various high entropy alloys with extra good mechanical and other property, but they are very prone to hydrogen embrittlement. And also, it is confirmed in additively manufactured alloys. This is the original paper from 2015, in which we show what means the predominance of one of the mechanisms. As you can see on the blue picture and on the right, the red picture, we have a very similar fracture appearance. But on the left picture, we have a little bit more ductile failure by microwave coalescence and some area fractured by transgranular due to heat, due to decohesion. On the red picture, you see that we have a little bit more transgranular, so both mechanism is active, and a little bit less microwave coalescence ductile failure. But what we can see on the blue and the right circle, the sharp drop of mechanical property appears in the case of the red picture, where we have a decohesion predominance, which means that on microscopic level, the material become brittle, while in the both cases, we have combination of ductile failure and combination with brittle failure, but a little bit more brittle area, which means that we have a decohesion predominance, which provide a sharp drop in mechanical property. And we show this, that practically ductility is almost always affected. As you can see, we have a Help predominance, we have a heat predominance, and we have a transition, which means that at some critical hydrogen concentration, we have a sharp drop of ductility and rarely the drop of ultimate tensile stress and yield stress. And we have a drop of hydrogen-assisted crack propagation. Generally, it means that our component will fail. Why? The definition of hydrogen-assisted cracking is hydrogen-assisted degradation of crack propagation resistance. And that's happening when we have a heat predominance and never when we have a Help or other plasticity-mediated mechanism predominance. That's the reason why it's extremely important to define and map, depending on hydrogen concentration, microstructure characteristic, and stress straight, the mapping of active mechanism in different material and to detect that transition. I will just give a brief hint about new concept. Apart from Help+Hede model, we also introduced in 2021 microstructure-dependent local heat microincident concept together with a researcher from Australia, and more recently, microstructure-dependent heat-prone traps concept. As you can see, there are a lot of papers with international authors. Here, the list of 10 papers published between 2019 and 2024 related to development and final definition of so-called unified Help+Hede model for all metallic materials. This is the overview paper for 2019. We show what's happening. Help+Hede, critical hydrogen concentration. At low and medium hydrogen concentration, we have plasticity-mediated mechanism, Help+Hede, and Help-mediated heat. We have a challenging condition when we have a transition between Help+Hede and we have a heat dominance, which means that we divided the fracture into so-called plasticity-mediated fracture modes, where the local critical hydrogen concentration is trap site is mediated by hydrogen and hence plasticity by some of the mechanism. And then at a high enough critical hydrogen concentration and general concentration, we have so-called decohesion fracture control mode, which means that we still don't have a pure brittle failure. We still have some area and some activity of plasticity-mediated mechanism, but from engineering point of view, they become negligible. So the effects is negligible on microscopic level, and the materials start to behave in a pure brittle manner, apart from the fact that we still have some remaining plasticity of metal. This is the local microheat concept. As you can see, depending on concentration, we have MVC, which means that we have a plasticity behavior of material and enhanced plasticity due to hydrogen, but we have a local spots in the microstructure where decohesion appeared. With the increase of hydrogen content, the number of that red locations increase. And at some critical hydrogen concentration, the number of local heat microincidents in microstructure, which is microstructure dependent, became high, that the heat dominance is due to accumulation of high enough number of local heat microincidents, a statistical phenomena, throughout the whole volume of the sample. In that case, we have a non-Help mediated heat, which means that plasticity enhanced mechanism become absolutely negligible, and we can call that pure decohesion phenomena. While still we can find some area, as you can see on this picture, failure by ductile failure and by hydrogen enhanced plasticity mechanisms. This is the confirmation of that. Yellow area are microheat incidents. As you can see, when we increase the hydrogen content from 2.88 to 2.95 in a very narrow range, we have an increase of microHede incidence area in a number and the size of that area. And then we have at some critical hydrogen concentration, pure brittle failure with negligible effects of Help or other hydrogen-enhanced plasticity mechanism. Hede-prone traps talk about that location which are prone to decohesion depends on microstructure. It could be precipitates, triple grain boundaries, voids, phase boundary, interface boundary, slip planes, grain boundary, as is shown here. So the concept of designing a hydrogen embrittlement resistance alloy is to control twin boundary, nanoprecipitates, and ground boundary in our material, which means to have as less as is possible hydrogen-prone, decohesion-prone locations in microstructure. What does it mean? It means that we have a locally high hydrogen concentration at that microstructural specific area. We have a decohesion incidence, which means that we have a initiation of local micro-cracking. Here is our review paper, which show the activity of particular mechanism. You can see here the change of failure mode, depending on the Help predominance, depending on the condition when Help is in competence with Hede, and then we have Hede much larger than Help. You can see the change of microstructure. You can see the drop of ductility. Also, we published microstructure dependent Hede-prone area in various type of steel. As you can see, we have cases of Help dominance and microstructure features, lead, martensite, ferrite, bainite, Hede dominance, Hede-prone locations, MNS inclusion, ferrite, pyrrolite for high-strength steel, for low-carbon steel. We are doing that to map the active mechanism in various steels. So, the conclusion, I already told you everything. Local Hede microincidents talk about Hede-prone traps and a new Hede-prone concept, which represent the essence of our unified Help+Hede model. Once again, not only Help, but Help plus other plasticity-mediated mechanism on one side, and on the other side, decohesion. Why? Engineers thinks that decohesion is dangerous. Why? When we have a Hede mechanism activation, we have a failure of the component, and not due to Help or Hsiao mechanism. So the experiment of observing both hydrogen embrittlement mechanisms simultaneously, which is the essence of our Help+Hede model, represent a significant challenge. Experiments, a way to precisely measure the hydrogen concentration and a local microstructure level are missing, and we need some new experimental techniques in order to reveal at which hydrogen concentration on local and global level that transition between mechanisms according to Help+Hede model appears. Thank you.